So today's discussion is going to be on Diff Eqs and RC circuits. I think there's going to be a lot of math introduction today. So I'll be spending a lot of time just going over some math, and I personally believe, some might not, but that the math is more important than the actual circuitry here. So especially because the math you're going to be using today is going to be bleeding into the next couple weeks and even the next couple months. So the Diff Eqs you learned today will go a long way. And the RC circuits, in my opinion, are just flavor text on top of all the math. So I know there were a couple of issues with people getting access to watch the lectures, but that is completely okay because we're going to be doing a lot more math than the actual stuff going over in lecture with all the transistors apparently that went on. So just a recap of what Diff Eqs are. A differential equation is just a way to relate a function x of t and any of its derivatives. So one example of this is dx dt is equal to lambda x, where again, x is some function of t. And another example of this is x prime of t is equal to 4x plus 7. And I think some people like to use certain notation over the other for differential equations, like dx dt is one way to write the derivative. X prime is another way to write the derivative. And I know some other people like to use x dot, but as a whole in this class, we're going to be mainly sticking to dx dt. And if I want to use shorthand, I'll use x prime. And as a whole, there are a bunch of ways to write out differential equations, and a lot of these differential equations are going to be talking about some underlying physical behavior of some sort of system. In our context, it's mainly going to be circuits, but in later parts of the course, you'll see how to write differential equations for things like the position of a car, or I don't know, so like a pendulum or so and so forth. So differential equations are really a way to model something physical in the real world. And just a foreshadow of what's to come later, we're mainly going to be looking at simple differential equations like these today, but later on, we're going to be looking at higher order differential equations. And we're also going to be looking at something called a vector differential equation, where we have the derivative of a vector is equal to a matrix A times a vector plus B. So this is going to be I think in the next 2 weeks coming up. And these are called partial differential equations, and we're not going to be talking about those in this class, but if you've ever taken physics, you might see those a lot. So yeah, that's what's to come. And these are just what differential equations are. And with any differential equation, we're interested in something called the solution. So the solution to a differential equation, whenever you're given some equation, normally you think of some solution as a variable, but here it's kind of different, where the solution is in fact a function x, where the equation is true for all values of t. So the terminology is a little different, and it might take some time to get adjusted to this new I guess syntax or methodology. So if you're given something like dx dt is equal to lambda x, the solution here is going to be a function of x. And in this case, I can tell you it's e to the lambda t. So I know I said a lot in the past minute, but do we have any questions about anything I talked about in this slide as a whole? Okay, moving on. So the main focus of today is going to be on something we call first order differential equations. I see some of you smiling here. And a first order differential equation is something that only involves the function x and its first derivative. So the two common forms you're going to see today are of the form dx dt is equal to lambda x, and then dx dt is equal to ax plus b, where b is some constant. And I think starting next week, you'll see something of the form dx dt plus ax is equal to some function of t, but that's for next week. But these are all considered first order differential equations because they all involve the first derivative of x and x. And with any sort of differential equation, we have something called the initial condition. And the initial condition describes sort of some physical like parameter where have we started initially in our like instance of a system. So it lets us describe a particular instance of the solution. So it's essentially defining where we start our function x of t from. And initial conditions are very important because they essentially let us solve our differential equations. And we'll see in the next couple of slides how initial conditions play a role. So any questions about first order differential equations and initial conditions? All right, moving on. So again, today is going to be a lot of math. Might get a little dry, but it is what it is. And it's really setting up stuff for later. So we're going to be looking at two, I think, really important examples here. And these are first order differential equations in their common form. So you can kind of see this as a differential equation of the form dx dt is equal to lambda x given some initial condition. And you might have recalled from lecture how to solve these differential equations, but if you don't remember, we're going to quickly go over how to solve these. And the way we're going to solve all of these differential equations are going to be through some methodology that we call guess and check. And there are other ways to solve differential equations, but for today, we'll mainly stick to guess and check. So the way guess and check is going to work is we're going to guess some function, x of t is equal to k e to the lambda t, where k is some arbitrary constant. And once you give a guess, you always got to check whether your guess works. So if we were to split this up, this is our guess stage. We guess some function. And now we check whether our guess works. And what I mean by check is we check whether it satisfies this differential equation. So the way to check whether something works is just to take the derivative, since we have dx dt. So the derivative of this function, k e to the lambda t, is just going to be equal to k lambda e to the lambda t, since the derivative of e to the lambda t is lambda e to the lambda t, and k is just some constant. And from here, we can rearrange terms to show that this is in fact equal to lambda times x of t. Since x of t, we had guessed, was equal to k e to the lambda t. Might seem like magic at the moment, but the more you practice this over and over, the more familiar this will become, and the more you'll take this as law. So, any questions about the guess and check process so far? Okay, and I know from, yeah, Allison asked the question I was about to ask y'all. How did you come up with that guess? So I think we'll talk about this in a later slide. And we can first claim that this guess that we came up with works. So we can claim that our guess works, and we'll later show that our guess in fact is unique. So if it's unique, it's the only thing that works, and that's why it works. And I guess some more intuition on how did I come up with that guess? Well, it's really kind of this intuition where if you're looking for a function where dx dt is equal to x, the function that satisfies this relationship is x is equal to e to the t. So if you kind of take this as law or this as like truth, you can kind of build up this guess over here. And I guess notice here that like multiples of e to the t all work, in the sense that like if you were to have k e to the t, then dx dt is equal to x as well. That's kind of the intuition behind the guess. All right, so if that's all clear, let's move on to the actual solving of the problem. So here we notice that lambda is equal to 3. So let's try and guess x is equal to k e to the 3t. And again, the verification is all from here. So we just showed that our guess works. And now you might ask, where do we go from here? We're kind of stuck, right? Like, you start with your guess, but how do you actually solve this differential equation? And the way you're always going to solve these differential equations after you guess and check is to plug in your initial condition. So you're given this initial condition of 5. So what we do is we just plug in x at t equals 0. And this tells us that this is equal to k e to the 3 times 0, which is just k e to the 0. And since e to the 0 is 1, this is equal to k. But we know that x of 0 is equal to 5, so k is equal to 5. And since k is equal to 5, we know that our solution is in fact 5e to the 3t. So do we have any questions about this so far? Might seem like magic at the moment, but I think the more we try this, the more it'll make sense. And just to recap the overall process, you guess, you check, and then you plug in your initial condition. All right, and our second example is kind of similar to the first, but it's a little bit more complicated because we have this +4 term here. And this +4 is kind of forcing our differential equation to do something else. So I'm going to briefly erase what's over here. And it's going to employ a new strategy. So if we're given something of the form dx dt is equal to lambda x plus u, given some initial condition, your first thought might be to try guessing and checking this value up here. So if you were to try guessing and checking, you would in fact show that lambda k e to the lambda t is equal to lambda k e to the lambda t plus u. And if you cancel both sides, you would show that u is equal to 0, but in this case, u is non-zero. So this is a contradiction. So this means our guess doesn't work. And if our guess doesn't work, well, is all hope lost? Well, we can actually improve our guess. So I'm going to tell you right now that something better to guess is something of the form k1 e to the lambda t plus k2. And it's very similar to the first one, except we just add a constant. And you're not expected to know how to come up with these, but like, these are just some like, I guess it's some like intuition behind like why it is the way it is. Like, you have some extra constant added here since you have some extra constant added here as well. And we can in fact verify that our guess works by just taking the derivative. And in fact, I'm gonna do this over here now, where we're gonna solve this differential equation up here by, I'm just gonna move my work over here. Sorry for all the confusion, but like, we're gonna start with guess x of t is equal to k1 e to the minus 2t plus k2. So k1 and k2 are scalars, and we want to solve for these scalars. So it's really going to be similar to solving a system of equations, similar to like what you do like with Gaussian elimination kind of. So we're going to take the derivative, And you can actually show that this is equal to negative 2k1 e to the negative 2t plus the derivative of a constant. But remember that the derivative of a constant is equal to 0. And then let's take a look at negative 2x plus 4. And negative 2x plus 4, well, what we're going to do here is we're going to plug in our guess into x. So this is going to be negative 2k1 e to the negative 2t minus 2k2 plus 4. So do we have any questions about what I've done so far? I know the second step here might have been a bit confusing. I know some people had questions in the earlier discussion, but
Could you just say again what you did in that last step?
yeah, okay. So I took the right-hand side, minus 2x plus 4, and I just plugged in the guess for x. So we have, I just plugged in k1 e to the minus 2t plus k2 is as x. Does that clarify things? I haven't done anything too complicated yet. I just plugged it in. And Alina asked a really great question. Don't we have too many variables now? And we do have two. Sorry, were you going to say something?
Would it make sense to put the x prime of t equals negative 2x plus 4 in front of that bottom equation so that you have two equations?
Yep. Exactly, yeah. And that's what I was about to do next. So to answer Alina's question, and this was leading on to my next step, now that we understand what these two quantities are, we're just going to set them equal to each other, since the differential equation told us that these two quantities are equal. So we know that negative 2k1 e to the minus 2t is equal to negative 2k1 e to the minus 2t minus 2k2 plus 4. And if you notice that these two terms over here are equal, so you can in fact cancel them from both sides. And this tells us that negative 2k2 plus 4 is equal to 0. Which means k2 is equal to 2. So we had too many variables, but luckily we're able to get rid of some because they were equal to the same thing. So now that we solved for k2, we're going to go back and solve for k1. So this is kind of like similar to back substitution, where now we can say that x of t is equal to k1 e to the negative 2t plus k2, but we know that it's equal to 2. And the way we can solve this is to just plug in our initial condition, similar to what we did up here. And I'm just going to skip some steps since we know that e to the 0 is equal to 1. So from here, we can conclude that x of t is in fact equal to e to the minus 2t plus 2. So do we have any questions about the whole process? I'm not 100% sure how much of this was actually discussed in lecture, so could you clarify the left side of the rightmost last step? Talking about, wait. Yeah, so the minus 2x plus 4, I've just plugged in x equals k1 e to the minus 2t plus k2 as x here. So then if I were to write out one more step, I could say that this is equal to minus 2 all times I think it'll make more sense if you put x prime equals minus 2 x plus 4 in the bottom right equation. And yeah, I think here, perhaps we should say that like x prime is equal to minus 2x plus 4. But essentially, how would you show the check line for the part above? I think the check line was kind of right here, where we set the two equal to each other. So once we set these two equal to each other, we check that this is equal to, we check that minus 2k1 e to the minus 2t is equal to this quantity, plus this quantity over here, minus 2k plus 4. And we ended up with a statement saying, this is only true when k2 is equal to 2. So I don't know if that explains it well, but like the check step is where you take the derivative, set it equal to the right-hand side, and verify everything that needs to be true. So over here, it was quite simple because it was just taking the derivative and setting it equal to lambda x of t, but over here it's a little more complicated. Because we have some conditional check where this is only true when k2 is equal to 2. And in fact, you could plug in this guess into this differential equation here above and verify that it's true. And I'm not going to do that here since we don't have enough time, but all right. So hopefully that clarifies most of the questions we had. And kind of to relate to like what we were all doing here, if we're given any sort of differential equation of the form x prime plus ax is equal to b, if b is equal to 0, we often call this a homogeneous differential equation. And if x is equal to k, in other words, if the initial condition is equal to k, we're going to say that the solution is going to be equal to k e to the lambda t. Or in this specific format, notice how this is different from x prime is equal to lambda x plus u. We're going to write this as k e to the minus at, since we can move this a x of t to the right side. And again, this is very similar to how we guessed. If we guess x of t is equal to capital K e to the lambda t, this tells us that capital K is equal to lowercase k, since x of 0 is equal to lowercase k. Perhaps it's easier if I use a different letter. I'm going to call this a. And for the second case we had up here, where b is not equal to 0, or u is not equal to 0, we call this a non-homogeneous differential equation. And if we're given some initial condition, the solution is always going to be of the form x of 0 e to the lambda t plus u over lambda e to the lambda t minus 1. Again, this is assuming dx dt is equal to lambda x plus u. And if you're curious how this ties into our guess that we did, if we were to guess x is equal to a e to the lambda t plus b, then comparing with our true solution here, this would actually tell us that x of 0 plus u over lambda is our a, and u over lambda is our b. So the formulas I just gave you are just like general formulas that'll always work given a differential equation. And the guess and check method is more just to like get you like this intuition of like where this solution here is coming from, or where this solution here is coming from. So do you have any questions about the whole process as a whole, whether it's guess and check or it's like the solutions that we gave up here?
Sorry, what's u?
Yeah, so u is some constant over here.
How is it related to the equation at the top? Is it b?
Yeah, it's b.
Okay.
So if I were to use the b form, then this would be like x of t is equal to x0 e to the minus at. And then this should be minus b over a e to the minus at minus 1. And the only reason I used lambda and u is because there is some underlying connection between differential equations and eigenvalues, but we'll talk about that at a later time. So, all right. Do we have any other questions?
Oh, why aren't you simplifying this equation further? Because like you could combine the e to the negative at terms. Is there like a reason that we're choosing not to?
Yeah, actually, so I think the reasoning might not be as clear today, but like essentially the idea is that if you remember for the homogeneous differential equation, you were able to see that like the solution is x of 0 e to the minus at, right? So for the non-homogeneous case, you can actually kind of see it as the homogeneous case plus some other forcing term. And if you've taken Math 54, you might recall that like if you have some system of equations, you can always write it as like the homogeneous solution plus a particular solution. So that's kind of like the idea behind it. And we'll talk about this, I think, in a later lecture.
Where does the lowercase a come from?
From x prime plus ax equals b, just from here.
Oh, thank you.
Yeah. Yeah, I might have like made it extra confusing with all the extra things I defined here, but like I think to clean it up, let's just stick with this. And I'm just gonna erase all of this. And stick with what's up here. All right, and I know I've spent a lot of time just talking about this as a whole, but like, I think as a whole, like, the problems that we're gonna do, like, coming up are all just gonna be set up the differential equation, and then from there, we're just gonna like use these facts, like, that we kind of just like spend a lot of time here deriving. And I think the solutions will go into the full derivation, but like in practice and on like an exam, I think you should be able to like quote these results. So I'm just going to take the more practical approach of just quoting results as we go, since like we are engineers. And I think the last remark I want to make before actually diving into the worksheet is on the uniqueness of all of these differential equations. I know someone earlier asked, like, how do we know our guess works? So
I had a question about that last slide.
yeah.
So you're just defining big A and big B as those terms, but simplified?
Yeah, so I guess the better way to connect this is that, like, what I'm trying to say here is, like, if we were to guess a solution of this form, A e to the lambda t plus B, we're always going to get the fact that, like, A is equal to x0 minus B over A, and B is equal to B over A. Like, this is just always going to be the case. Like, these two quantities are always going to be equal, just like by, like, quote unquote random chance, but really by the uniqueness theorem that I'm going to talk about.
Okay, thank you.
Yeah, and quest material, I honestly have no idea. I know, like, Ramsey and Max are supposed to have a post, like, ready, but, like, hopefully by, like, today or tomorrow. Anyway, this kind of begs the question that all of you have been asking, like, why does all this work? Why is, like, guess and check working the way it is? It, like, all seems like black magic right now. So it works because of this thing we call the uniqueness theorem, which says if you're given a differential equation of this form, we're always going to have some unique solution. And this unique solution is going to be of this form. And there's a proof for this uniqueness theorem. It used to be on the homework, but it was a little too hard. People complained a little too much, so we took it out for this semester. But if you're curious about the proof of it, like, definitely, like, stop by, like, OH, and I'd be more than happy to, like, go over it with you as well. So, and if you ask any of the other TAs and ask about the uniqueness theorem, I think they'd be able to, like, go over it with you as well, since it was covered in previous semesters. All right, so any more questions or talk about the uniqueness theorem? Okay, so I think moving on to the worksheet as a whole, it's going to be a lot of setup, and I'll give you some time to work on this on your own as well. But for today, we're mainly going to be looking at RC circuits, and this might be a little bit, like, off of what, like, lecture was doing. I know, like, lecture was trying to, like, get you to, like, look at a, like, transistor inverter and get you to, like, write differential equations for these. But you can in fact show that all of these, like, inverters can be reduced into an RC circuit with a single resistor and a single capacitor. So today we're mainly going to be looking at how to solve these circuits with a single resistor and a single capacitor. So do you have any other questions about the overall plan for today? I think we're going to mainly look at, like, how to solve these circuits. And if we have time, we're going to look at, like, how to graph the solutions as well. So, okay. So first question asks you to somehow relate the current across this capacitor, IC of t, to the voltage across this capacitor, VC of t. And the way we're going to do this, we're going to first write everything we know. And we know that Q is equal to CV, hopefully from 16a. And we also know that, like, the current across any, like, I guess, like, wire is equal to the derivative of the charge. Hopefully this is all familiar. So given these two facts, we can take our first equation over here, Q equals CV, and we can just take the derivative with respect to t. So dq dt is going to be equal to the derivative of this term over here. Notice that it's a product of two things, but since c is a constant, we can just pull the constant out of the derivative. And unfortunately, VC is not a constant. It's some, like, variable voltage. So it's going to be equal to C dVC dt. And lastly, we can use the fact that I is equal to dq dt and plug that into here. So I C is equal to C dVC dt. Okay. Do we have any questions about part A? All right, if we don't have any questions, let's take a look at part B. For part B, I'm gonna explain what you need to do and then split y'all up into breakout rooms and you can try to solve this together. And what it's asking you to do is to use node analysis, so everything you remember from 16a, and to write a differential equation for the capacitor voltage Vc of t. So yeah, it just boils down to node analysis. And if you don't remember the steps, I think the steps are to identify the nodes, to write KCL, and then to use some sort of like Ohm's law. And here you're going to need to use Ohm's law plus the relationship we derived in part A. So, all right, any questions before we split up into breakout rooms about what we need to do?
Can we just use N0 as a datum to be ground?
Yes, good point. I did this in the previous discussion, but I didn't do this here. Yeah, I'm just going to label N0 as ground to make everything a lot simpler. Okay, any other questions before we move on? Okay. If not, I've just opened up all the breakout rooms and I'll just be dropping by if you have any other questions you want to ask. All right, looks like people are starting to come back. Were people able to get the full differential equation? I know one group got it, but just wondering how the other groups are doing. All right, let's go over this together. So step one is to identify all nodes. I think they've kind of done that for us. So I'm just gonna say this is done. And step two is to write out KCL. So we know that IR is equal to IC. Should be a relatively straightforward step. And lastly, we need to use our IV relations. And in 16a, these were all Ohm's law equations, but now we're going to see that like this capacitor equation over here is really important. So this is going to be another IV relation you're going to use a lot. So if we were to substitute for IR, we know that IR is equal to, from Ohm's law, V of t minus Vc of t all over R. And we know IC is equal to C dVc dt. So we can just equate the two. And this really tells us our differential equation. And I think the last step is to always just like simplify. And we're going to see like why we want to simplify this. So any questions about the overall process? All right, so some of you are still copying this down, but like I will be posting like slides after as well. So
Sorry, when you say RC there, what are you referring to?
like RC over here,
Yeah.
just the product of like the resistor R
Oh,
and
yeah.
the
Okay.
capacitor C.
The
Yeah.
Yeah. Okay.
So now the last part of the question is going to say we charge our capacitor to VDD. So VC of 0 is equal to VDD. And now we're discharging the capacitor kind of through this resistor. And we want to solve the differential equation. So first step, let's just take what we have. We already know this fact over here. And we're also given the fact that V of t is equal to 0 for all t greater than or equal to 0. So really, we can simplify the right-hand side over here to 0. And from here, it really is just plugging in what we knew from way back. So also know that like given dx dt plus ax is equal to b, that x of t is equal to this formula that we derived earlier in discussion. And we know that Vc of 0 is equal to VDD. So it remains to just plug everything in. And perhaps, yeah, this form is fine. It's just a little hard to work with, actually. I think sometimes it might be easier to use the first form I derived, where it's like I think this form might be a little easier here. So this is going to be VDD. And I think actually before we go into anything, let's just identify everything. So 1 over RC is going to be A and B is equal to 0. So actually for here, I don't know why I gave you this formula over here. We could have just used the much simpler formula that like the solution here is just x of t is equal to x of 0 e to the minus at. But again, if you were to plug it all into this formula over here, you'd have gotten the same result. And with all this in mind, since you know A is 1 over RC, you can just plug in for A and you'll get VDD 1 over RC times T. So any questions about the first part? All right, and the second part, I think our equation here will be much more useful. Let's copy over the equation. Let's also copy over the differential equation we had. And the second part is a new scenario. So the new scenario here is that V of t is equal to VDD for all t. And we want to, again, solve for the differential equation given the initial condition of 0. So we're assuming the capacitor is initially uncharged. So if we were to actually evaluate V of t here, we would see that this is equal to VDD over RC. And this would be our B. And after that, we're just like plugging into our solution. So we're just plugging in VDD, e to the minus 1 over RCT, minus, and then B over A is just VDD over RC, all over 1 over RC, e to the minus 1 over RCT, minus 1. And if we were to simplify all of this, I'm sorry, x of 0 is 0. Since VC of 0 is 0. This just tells us that we have 0 minus VDD, e to the minus t over RC minus 1. Or we could write this as VDD times 1 minus e to the minus t over RC. And see a couple of questions in the chat, one of which asks, how did we get the answer for VC? And I think all of this just comes from like plugging in the solution for A and B that we kind of derived like 5 or 6 slides back. So it really is just like a lot of heavy lifting in the earlier part where like we like to spend a lot of time understanding why these work the way they do. And then we were able to write out general like solutions for these differential equations. And now, given any new differential equation, we can always just identify what A and B are. And from there, just plug in a known solution. I think the solutions will do this in like an alternate way where like you basically rederive everything that you did up here. So if you do look at the discussion worksheet once more, it might be good to just like rederive all these like formulas that I gave you here using the same method of guess and check that we did up here. Okay, any questions that we had aside from this?
So in circuit terms, C is how the voltage drops over time, and D is how it charges over time.
Yep, that is exactly the case. And it is 12 o'clock. Y'all are free to leave, but I'm just gonna give like 2 drawings of like what you really need to take away from question 2. And similar to what, I don't know who it was that made that comment, but was saying, we're assuming that we're initially charged and we're discharging. So in the discharging case, recall that our solution was equal to VDD e to the minus 1 over RCT. And if you were to plot these on like Desmos, you would get a curve that looks like this. That eventually decays to 0 in the limit. And in the charging case, this was when we were initially uncharged and we're attaching a voltage source here and we're charging up this capacitor. We would get the opposite shape where we have some asymptote at VDD. We start at 0 because we're initially uncharged, and we're going to rise up to VDD. So those are the main takeaways from this problem. And I think because the professor also didn't get the chance to talk about time constants, like I'm not going to talk too much about that either. So I think we will call that an entire discussion. So if you have any questions you want to ask, feel free to ask. I'll stick around for the next like 10 minutes or so. I know we went through a lot, so I think definitely in your own time, definitely take some time to like look back at like the discussion worksheet and like to take a look at more like differential equation examples. You'll see some more in your homework coming up on Thursday as well.